Hey, Conceptual Physics, how's it going? It's Mr. Burkhart with his COVID haircut and his COVID beard. And I'm going to do my best to answer some of your relativity questions from last week. Um, I loved them. A lot of them are really, really good questions. Um, and I want to try and do my best to go through that, a little summary of relativity myself, to hopefully put it in terms that maybe make it a little bit clearer. I thought that was a great video that went through a lot of it, but relativity is a really kind of complex subject. So it does require, thinking about it a little extra and maybe going through some details here and there. So one of the first questions I got, which was a great question, was why is the speed of light the same for all observers? And the answer to that is it just is. It's one of those fundamental rules of the universe. It's how our universe is built. So if you don't like it, you kind of have to take it up with who or whatever made the universe. For some reason, everybody observes light to be 300,000 meters per second. That means so it goes 300,000 meters every second. And that's the same regardless of how fast you're moving. So if I'm not moving and someone else is moving and we both see the speed of light as the same speed, that has some interesting implications. Which brings me to time dilation. So one of the things that happens in order for the speed of light to still appear to be the same speed for me as for somebody who's moving is, if you think about a really basic speed equation, v is equal to d over t, we have to manipulate either d or we have to manipulate t in order for the speed to be the same if I'm already moving and or if I'm not moving and somebody else is moving. So one of the first things to get manipulated is time. So time actually does change depending on your state of motion. These are real-time effects, and I think the best proof that it happens and that we have to take it into account is that our GPSs work. The satellites are way up in the atmosphere, and they are, or outside of the atmosphere, and they're moving at one speed and we're moving at a different speed. And if time dilation wasn't taken into account, your GPS would be useless. It would say you're in Madagascar someplace. I have to find the exact stat, but I want to say it'd be off by 15 miles in 8 minutes. Like it's a pretty extreme change. So time dilation is a real thing that we have to worry about when you're doing that sort of thing. Okay, that explains what it has to do with speed. Oh yeah, and effects. Time dilation happens to a very minor extent when you're sitting, and then when you get up and start walking around. As soon as you start walking around, time is moving differently for you. Now, is it a huge change? No. I could always push out an equation and have you guys, figure out how many fractions of a second your time dilates, but it's not. It's really not worth the math trouble. Let's see. Another great question we got were speed perspective questions. So like questions about, well, if the two kids were throwing a ball back and forth and it was 10 miles an hour and the car was moving 50 miles an hour, was the ball actually moving 60, or was the ball moving 10, or what speed was the ball moving, or do we have to take the Earth's speed into account? And the answer for that is it all depends on your perspective. That's kind of the problem with, or that's kind of like the idea behind relativity, is depending on your perspective. Time is relative, and speed in some cases is also kind of relative. It depends on your perspective. So if you were inside of the truck, the ball was moving 10 miles an hour. If you were way out, looking at Earth as a planet, the ball was moving a different speed. It wouldn't just be 60 miles an hour. You'd have to take into the spin of the Earth into account. So there's that as well. People were asking, objects contract at c. Again, think about v is equal to d over t. Okay, so when you get to c, or you get close to c, you're no longer dilating time as much. So you have to change something else. So in the dimension you are traveling, objects will actually get shorter. Um, and that is all down to v is equal to d over t. So if the t is not changing that much anymore, I guess the d has to change. So your distance has to change. So that's another interesting kind of issue. Somebody asked, why would it take infinite energy to travel the speed of light? And the reason why it would take infinite energy is as you're approaching the speed of light, remember E is equal to mc squared. As you're starting to approach the speed of light, you begin to gain mass. And because you begin to gain mass, it actually gets harder for you to continue to speed up. So you have to keep putting in more energy. And it's an exponential issue so that you keep going. The closer and closer you get to the speed of light, the more and more mass you get, the harder and harder it is for you to get moving to that speed of light. So at some point, it's not practical to go to the speed of light. Which brings me to another question I got. Will we ever get an object to go the speed of light, or have we ever gotten an object to go to speed of light? Now, we get particles to go the speed of light all the time, tiny little bits of matter. And we get them to go the speed of light, and then, as you learned with the particle accelerators, they gain a bunch of mass, and you can smash them into each other. But as far as like a baseball, can we get a baseball to go the speed of light? No, probably not. Because again, the more you speed that ball up, what mechanism would you use to speed it up? You have to worry about air resistance. It would reach a terminal velocity at some point. The faster you get it to go, the more massive it's going to become. At some point, it becomes kind of impractical. Okay, and then another really interesting question that you guys gave me, which was neat, was what happens if the universe stops? What happens if you keep an object completely still? So you guys were fascinated about the part where, okay, your universe is always moving, right? We're always moving. What happens if we didn't? So I can say for the, at least for our immediate fate on Earth, let's say that our solar system stopped moving. If Earth stopped orbiting, we would follow what you guys would call gravity, right? We would follow the curvature in space-time, and we would start drifting towards the sun, and eventually we would fall into the sun, and the sun would burn us up. Vice versa, the sun is actually, because of our circular motion, we're always falling towards the sun, but we're never making it. We've learned that before. That's called orbit. The sun is orbiting around the center of our Milky Way galaxy. So, it's not just that the sun would then be, just chilling for the rest of its existence. It would start drifting towards the center of the Milky Way galaxy into the supermassive black hole there, and eventually it would fall into that. And so would every other star in the Milky Way galaxy. All right. So, I got to run for now. I got to answer a call on the live feed. But it's good seeing you guys, and I hope I answered your question.